Hello students, welcome to Inside Physics. In this session, we are going to discuss about alpha ray scattering experiment which is very famous and conducted by Rutherford. His two disciples and research associates Marsden and Giger are given some work by Rutherford in 1911. So, it is around 1911 the curiosity about the atom and its central part called nucleus and the structure of the atom is very much led by this scientist Rutherford, and the experiment has given a good results to actually explain the Rutherford's nuclear model of atom. So, what is about this experiment and what were the results he obtained? And the world is astonished by the facts that the nucleus is a central part of the atom and it was the tiniest of the particles. So, the space occupied by a nucleus inside an atom is very less compared to the size of the atom. So, because of the curiosity of the how the atomic model and what is inside the atom, so this is done by him with some experimentation, and we see what is happening here. So, this is bismuth 83214, a radioactive element which emits spontaneously alpha particles. So, these alpha particles are rays coming out of a natural radioactive element. So, these alpha particles are also called nucleus of helium atom. So, they carry 2 electrons and 2 protons. So, they are collimated as a beam. So, the alpha particles are coming out of bismuth element. So, they have actually come out like this, and they are collimated. What is the meaning of collimation? Means they are made into a beam, a thick beam of alpha particles. So, for that we used lead bricks which can capture the alpha particles which are moving all around, and the narrow passage between the lead bricks actually makes the alpha particles like a beam of alpha particles. So, here they carry an energy of 5.5 million electron volts. So, there must be some energy for a moving particle, and the emitted alpha particles are also moving out of bismuth atom with an energy of 5.5 million electron volts. So, here the energized particles will hit the gold foil. This is thin gold foil taken for this experimentation. How much thin the gold foil is? It is around 2.1 into 10 to the power of minus 7 meters. Very thin. Why that thinner is taken in this experiment means, so the thinner the element and the alpha particle will pass through, and there will be a passage through the foil. So, they will be deviated with the central part. So, the nucleus actually occupies very small distance, small space inside the atom. So, by kinetic theory of gas we came to know that the size of an atom is around 10 to the power of minus 10 meters. With this experiment, actually the size of a nucleus has come out to be around 10 to the power of minus 14 to 10 to the power of minus 15 meters. So, this is the size of an atom. Size means radius of an atom. This is the size of nucleus. That means size is almost taken as radius. So, compared to atom and nuclear sizes, it is almost 10,000 to 1 lakh times the atom is bigger. So, when the alpha particles are passing through a gold foil, the atomic number of gold is 79. So, it must contain 79 electrons and 79 protons. So, here the deviation, how will they deviate when they are passing through the thin gold foil? That means there will be an electrostatic repulsion between the alpha particles. What is an alpha particle? Helium nucleus. So it must, the nucleus must carry 2 electrons, that means helium is He24. Atomic number 2 means 2 electrons and 2 protons carried out by the helium. The nucleus contains 2 protons and 2 neutrons. So the alpha particles will actually collide with the nuclei of the gold atom. See, they actually colliding, I am using the word colliding, they actually don't collide, they come very near to the nucleus. Okay, why? Because they don't collide is there will be a force of repulsion between the gold nucleus and alpha particles, and by Coulomb's law we can calculate the repulsive force. What this is the formula to calculate the attraction or repulsion between two charges. So here Q1 Q2, that means what is Q1? Charge on the alpha particle 2e positive, and Q2 the charge of the nucleus of a gold atom, that is 79 E, or you can say Ze. Z is an atomic number of generalization by R. R is the distance between the two charged, how much close the alpha particle goes towards the nucleus, and they will definitely deviate because of repulsive force. The deviation is important here, because of the deviation of alpha particles when they are approaching the gold nucleus is the key to understand the structure of atom, what is there inside the atom. So almost 0.14% of the emitted alpha particles will be deviated actually by 1 degree. So very less, 0.14% are deviated by only 1 degree. So out of 8,000 alpha particles, only one is deviated more than 90 degrees, greater than 90 degrees. So why I am telling these details is to say that the deviation of most of the alpha particles is very negligible. That means almost they are passing through without any deviation. You can see by 1 degree, so they are actually how much percentage? 0.14. Greater than 90 degrees, one helium nucleus alpha particle out of 8,000, very less. Why this is happening? Because most of the atom is empty. Okay, and see here how the alpha particles are moving means with the kinetic energy they carry. So there is a distance between the nucleus of the gold atom and the alpha particle, that is called impact parameter. Impact parameter, which is represented by small b. Impact parameter is nothing but the distance between the nucleus and the initial velocity vector of the alpha particle. If alpha particle is starting like this, and there is an initial velocity for that, and that velocity is represented by some vector v. So the impact parameter is the distance between the velocity vector and the nucleus, gold nucleus. So if the impact parameter is less, means the alpha particle is approaching the nucleus much closer. So if the impact parameter is more, it is getting deviated without much going further, without reaching the nucleus of the gold atom. So impact parameter, see, if impact parameter is very less, that means almost touching the nucleus, the alpha particle rebounds. That means angle of deviation will be 180 degrees. The impact parameter is more. That means the angle of deviation will be around 90 degrees. See, how these deviations are detected, that is the question here. So, okay, alpha particles are entered into the thin gold foil which is arranged here. They go and deviated. I have seen this, see this. This is a backward scattering of very small fraction. Backward, that means when it is closely approaching the central nucleus because of repulsion, it is going backwards. And see this, it is actually after hitting the gold foil, it is actually deviated like this. There is a detector which is a rotating detector, and this is a zinc sulfide coated screen. So when the alpha particle which is deviated after passing through gold foil hits the ZNS zinc sulfide screen, it produces some scintillations, that means some spark. So you can see the sparks with a microscope. This is called detector, which can be rotated around the screen. So why this is in circular shape means you can see that all the deviations will happen like this when the alpha particles are passing through the gold foil. So the as a function of angle of deviation, we can understand the distribution of the deviated alpha particles. So the function of angle of deviation, as a function of angle of deviation. So this is how we actually understand the scintillations happened on the screen with the microscope called as a detector. So how the, if we plot a graph between the angle of deviation and the number of alpha particles deviated, the graph will look like this. So you may take the angle of deviation as 20, 40, 60, 80, 100, 120, like that. Okay, and the number of alpha particles, you can take it as 4, 10 to the power of 5, 10 to the power of 6, and 10 to the power of 7. Okay, this is the alpha particles. So this is the angle of deviation. The graph will look like this. So this graph is, you can see that around this 90 degrees there is a fraction of 10 to the power of 2, very less. So most of the particles which are having very less deviation is in high number. If you can have some dots, the number of alpha particles like this, they will actually indicate the numbers and the angle of deviation. This is theta, angle of deviation. This is number of alpha particles deviated with these angles. You may have a graph like this. Okay, so this is the understanding and assumptions. You can say not assumptions, this is actually, it is a facts that's arrived at the end of this experiment by Rutherford and his two associates Marsden and Geiger. Okay, so what are the conclusions that we can have with the alpha ray, alpha particle, or you can take it as ray or particle, alpha particle scattering experiment. So see here, this is the why he has opted for gold foil, means why not silver, why not iron foil? So see, Z atomic number of gold is 79, which is probably very high compared to alpha particle, which is helium nucleus. So when helium nucleus, the alpha particle is actually compared to the mass of the gold nucleus, it is very less, right? The more the atomic number, mass is also more for the nucleus. So a tiny particle is, if we assume, hitting a large object, we can say that there will not be any effect on the heavy nucleus. So the effect will all on the alpha particle only. There will not be any effect because it's very heavy compared to alpha particle, and that is the thing is opted for gold foil. Okay, and why the angle of deviation for large number of alpha particles is very less means here we can assume that most of the atom is empty. So the electrons revolving around the nucleus will show a very little effect, small effect on the alpha particles entering into the atom, because the mass and the mass of the electrons which are and the the rotational kinetic energy carried out by electrons is very less, and there will not be any effect, and mostly the alpha particles will enter because there is a large empty space. So by these all the facts concluded by this experiment, the nuclear model actually is given to the Rutherford. He is the one which actually successfully proposed the nuclear model. What is new? Why it is nuclear? So here the electrons are revolving around the nucleus just like the planets around the sun, and the central part nucleus is just like the central sun, which is stable and very heavy. So that is why these assumptions will actually take us through to the nuclear model, and somewhat there are also some defects in this nuclear model, but most of the points, the atomic space and the heavy central nucleus are absolutely correct, and came out very correct with this experiment. That is about the alpha particle scattering. See, in the next session we will see some interesting more topics.